Hey everyone, welcome back. Today's explainer is all about decoding the invisible infrastructure that literally keeps our modern world connected. We're diving into Week 1 material, an introduction to routers and static routing. I want you to think of the entire global internet as this vast, incredibly complex postal system. Millions of packages or data packets are being sent out every single second, and they all need to find exactly the right destination. But, who's actually sorting all this mail, and how do they know exactly where to send it? Well, today, we're going to pull back the curtain on the fundamental traffic hops of the internet.
Here is our agenda for the explainer. Number 1, meet the Layer 3 router. 2, IP addresses and subnetting. 3, inside the routing table. 4, configuring static routes. And finally, number 5, the recursive lookup process.
So, let's kick things off with a pretty massive question. How does a lost packet of data actually find its way across the globe using nothing but a digital address? It's honestly kind of mind-blowing when you stop and think about it. You click a link, and instantly, a packet traverses miles of fiber optic cables, hops through multiple different networks, and arrives right at your screen in milliseconds.
Section 1. Layer 3 Router, the Network Master. Now, if you've studied any networking basics, you already know about switches. And switches are fantastic, but they operate at Layer 2 of the OSI model. That means they use physical MAC addresses to pass data around within the exact same local network, so internetwork. Routers, on the other hand, they operate at Layer 3, the network layer. They use logical IP addresses to make these intelligent decisions about how to connect entirely different networks together. Think of it like this. If a switch handles the mail inside your specific office building, the router is the fleet of trucks moving the mail between completely different cities.
Section 2. IPs and subnetting. Digital zip codes.
Okay, so IPv4 addresses are made up of 4 octets, separated by dots. Historically, these addresses were grouped into specific classes, A, B, and C. Class A was reserved for absolutely massive networks, assigning only the very first octet as the network portion, which gives us that /8 default subnet mask. Class B was for medium networks, and Class C gave us the familiar /24 mask for smaller networks, kind of like your home Wi-Fi. Now, while we use classless routing today for way better flexibility, understanding these historic boundaries is absolutely crucial for grasping how networks are sliced up.
And slicing networks up is exactly what subnetting is all about. It's simply the process of dividing a larger IP network into smaller, much more manageable subnetworks. So why do we actually do this? Well, a single massive network is incredibly noisy and, frankly, insecure. By subnetting, we cut down on that broadcast traffic congestion, and we can easily isolate groups of devices for way better security and efficiency.
But let's be real for a second. Subnetting math can be super intimidating with all the binary conversions. Fortunately, there's a brilliant math shortcut to calculate subnets way faster, and it relies on finding something called the block size. First, you just find the custom subnet mask value in your interesting octet. That's the octet where the actual subnetting is happening. Second, subtract that value from the magic number, 256. Third, whatever number you get is your block size. That means your new subnets will simply increment by that exact number.
Let's actually see that shortcut in action. Imagine we take a standard Class C/24 network, like 192.168.10.0, and we decide we need 4 subnets. We borrow 2 bits, changing our mask to a /26, which translates to 255.255.255.192. Using our handy shortcut, 256 minus 192 gives us a block size of exactly 64. Notice the resulting network ranges, 0, 64, 128, and 192. It literally works perfectly. Each subnet neatly provides 62 usable host addresses for our devices.
Section 3. Routing table. The router's mat.
So the map is drawn, our subnets are defined, but the router needs a master directory to read this map, and that is stored right in its memory as the routing table. When you log into a Cisco router and type show IP route, you're going to see a list marked with a bunch of different letters. C means directly connected. The router automatically knows about these networks because, well, it literally has a cable plugged directly into them. S stands for static routes. These are the paths that we, the network admins, manually type in. You'll also see letters like R or O for routes learned automatically through dynamic protocols. Oh, and don't forget the default route, represented by all zeros. That is the ultimate catch-all gateway of last resort.
This brings us to a really crucial point. How does a router decide which route to take when a single destination IP actually matches multiple entries in that table? It uses a rule called the longest prefix match, or LPM. The router is always going to select the route that has the most specific subnet mask. For example, if the router has a path for a /24 network and a path for a /25 network, and the packet matches both, the /25 wins. Why? Because it's a more specific, longer match. It's kind of like choosing directions to a specific house address instead of just general directions to the city itself.
But wait, what if two entirely different sources offer the exact same specific route? That is where administrative distance, or AD, comes in as the ultimate tiebreaker. AD is basically a value that determines the trustworthiness of the route source. And you definitely want to remember this. The lower the number, the better. A directly connected route has an AD of 0, meaning it is 100% trusted. A manually configured static route has an AD of 1. So, if a static route and a dynamic routing protocol both offer a path to the same destination, the router is going to trust the static route every time, simply because one is lower than the AD of any dynamic protocol.
Section 4, Configuring Routes, Taking Control.
Knowing that static routes are these incredibly trusted manual overrides leads us perfectly into actually taking absolute control of our network traffic. The basic syntax for configuring a static route on a Cisco router is honestly quite elegant. You enter global configuration mode and just type IP route, followed by the destination network you want to reach, its corresponding subnet mask, and finally either the next hop IP address or the local exit interface that the router should use to send the packet on its way.
Let's look at how this builds into a real-world command. Here we have IP route 192.168.2.0, 255.255.255.0, 192.168.1.2. What we're telling the router here is very literal. We're saying, hey, if you get a packet destined for the 192.168.2.0/24 network, I want you to hand it directly off to the neighboring router sitting at the IP address 192.168.1.2. It's manual, it's totally predictable, and it is entirely under your control. Now you might have noticed we actually had a choice at the end of that command. We can point to a next hop IP, or we can point to an exit interface. If we use the next hop IP, we're aiming at a specific neighbor's address. But if we use an exit interface, like say gigabit Ethernet 0/0, we're really just telling the router to shove the packet out of a specific physical port. Actually, using the exit interface is a bit faster for the router's processor, especially when you're dealing with simple point-to-point links.
But this raises a really fascinating scenario. What happens if you configure a static route using a next hop IP address, but that neighbor's IP address isn't directly connected to the router? How on earth does the router know which physical cable to push the data out of?
Section 5. Recursive lookup, finding the path. The router solves this puzzle using a very clever double-checking mechanism called a recursive lookup. It's essentially the router finding the path to the path itself. Here's how it works. Step 1. The packet arrives and the router looks up the final destination network, finding your static route that points to a next hop IP. Step 2. Because it only has an IP and not a physical interface, it literally has to consult the routing table a second time to find out how to reach that next hop IP address. Step 3. Once it finally resolves that next hop IP to a directly connected local interface, it forwards the packet. When you're configuring these routes, efficiency really matters. If you use next hop IP only, you're forcing the router to do that recursive lookup, which adds a tiny bit of CPU overhead. If you use exit interface only, well, there's no recursion needed. The router just fires it right out the port. But the absolute best practice for maximum efficiency and clarity? Combining them. Specify both the next hop IP and the exit interface in your command. That way, the router immediately knows exactly who to send it to and exactly which port to use. No guessing required. Okay, before we wrap up, I have to share one brilliant trick with static routes. It's called a floating static route. Take our standard command, but notice we added a 10 at the very end. That 10 artificially changes the administrative distance. By raising the AD from 1 to 10, this route suddenly becomes less trusted than a standard static route. So why would we ever do this? It creates a hidden backup route. If your primary route goes down, this floating route automatically floats right up into the routing table to save the day. It's a real game changer.
We have covered some incredible ground today, from the Layer 3 intelligence of routers all the way down to the manual precision of static routes. But I want to leave you with a provocative thought to chew on. Static routes are amazing, yes, but they're also incredibly stubborn. What happens to all your network traffic if a static route points to a next-hop router that suddenly loses power or just goes offline? The static route won't fix itself. Your traffic will literally just drop into a black hole. So how do we build networks that can heal themselves and find new paths automatically? Well, that is the exact problem dynamic routing protocols solve, and I absolutely cannot wait to explore that with you in our next explainer. Keep learning, stay focused, and I'll see you next time.